Hello everyone again to my YouTube channel. Today in this session I will continue the second part of linear programming. In the last session we discovered all the linear programming part of maximization and I show for you what is the advantage of linear programming is important to make us to give us the ability to make the right decision. So today I will show you the second part of minimization application using some application. Well, let's start with the first application. At university, Professor Seaman wished to employ two people, John and Mary, to create a paper for his class. John is a graduate student at Cairn, but 20 papers per hour. John earned $50 per hour for graduate papers. Mary is an postdoctoral associate and can grab 30 papers per hour, may earn $25 per hour for graduate papers. Each must be employed at least 1 hour a week to justify their employment. If Professor Prof. Siemens has at least 108 people to be graduated each week, how many hours per week should be employed each person to minimize the cost? Well, I try to summarize the problem like that. So here, what is the problem is to minimizing the cost of graduate paper. Well, I consider it x here. Variable is the number of hours per week John is employed, and y the number of hours per week per week Mary is employed. But we have the variables of John and Mary, and how much of hours should be worked to handle this problem of graduate paper. Well, the goal here is to minimizing this cost of the graduate paper. Well, well, the cost function here is to minimizing the cost of graduating paper for professor at this university. Well, we have C cost function equal to 50x plus 25y, and we have some constraint here. First one is x equal to 1, greater or equal to 1 because each must be employed at least 1 hour, at least 1 hour. For x, for y also, it should be greater or equal to 1. We have this constraint with the x because John graduate just 20 people and for Mary graduate 30 people. And lattice for this professor has 110 people to be graduated each week. Well, 20x plus 30y greater or equal to 100, and for x and y should be equal to 0 or positive. Well, I using this application of Pelpo to solve this problem. Well, I create firstly this variable x and y. Okay, and I create also this objective function. Okay, 50x plus 25y, and also I create those construct x greater or equal to 1, y greater or equal to 1, so 20x plus 30 y greater or equal to 108. Well, I apply the solver, I run it. So this is the solution I found. So based on this constraint, I want to minimize this constraint. This is the optimal solution. That means for John should work 4 hours and for Mary 1 hour, and the cost is $85. So the lowest cost is 85 hours. If John work just 4 hours and Mary 1 hour, this is the best solution based on this constraint. Well, let's continue with another example. So Professor Hammer is on a low cholesterol diet during lunch at the college cafeteria. He always chosen between two meals, pasta and tofu. The table below lists the amount of protein, carbohydrate, and vitamin each meal provides, along with the amount of cholesterol he is trying to minimize. Mr. Hammer needs at least 200 grams of protein, 960 grams of carbohydrate, and 40 grams of vitamin for each meal. Over this time period, how many days should we have the pasta meal, and how many days to tofu meal, so that they get the adequate amount of protein, carbohydrate, vitamin, and the last at the same time minimizing the cholesterol intake. Well, our goal here is to minimize the cholesterol for Mr. or Professor Hammer. Well, this is the information we have for this problem. Well, we have this protein. For pasta, we have 8 grams, and for tofu, we have 16 grams. Carbohydrate, we have 16 grams in pasta and 14 and 40 for tofu. And for vitamin C, we have 2 grams and 2 grams also in tofu. And the cholesterol, we have 16 milligrams and 50 milligrams in tofu. Well, I consider two variables. The first one is the number of days Mr. Hammer ate pasta, and the number of days Mr. Hammer ate tofu for y. The object function also is to minimizing the cholesterol, because here we have. So the function here is to minimizing this cost function c equal to 60x plus 50y, 60 milligrams and for 50 milligrams for tofu. So based on our constraint, we have 8x plus 60y greater or equal to 200, because here in protein we have 80 grams and 60 grams, and Mr. Hammond needs also at least 200 grams of protein. Okay. So for the reason we're writing our constraint like that. We have also 60x plus 40y greater or equal 916 grams of carbohydrate, and for vitamin we have 2x plus 2y greater or equal 40 grams of vitamin C. X should be greater or equal to 0. Well, we're writing our algorithms here. This is our objective function. We create also firstly the two variables x and y, and also we created our object function here is to minimizing the protein, because as we see here we have 16 and we have 15. So both of both. Well, we create also our constraint here as we see. Okay. It's in constraint. Well, I apply my solver, yeah, and this is the result. So to minimizing this cost of cholesterol based on this constraint, Mr. Hammer should eat 8 days should eat the pasta and 12 days for tissue. And the latest measure of cholesterol is 1080. Okay, last measure or the small measure of cholesterol is 1080 milligrams. Okay, well, this is the optimal solution we have based on all these constraints. Well, I hope that's clear for you. Well, let's continue with another example. A diet is to contain at least 2040 units of vitamin, 1800 units of mineral, and 1200 calories. Two foods, food A and food B, are be purchased. Each unit of food A provides 50 units of vitamin, 20 units of mineral, and 10 units of calories. Each unit of B provides 20 units of vitamin, 20 units of mineral, and 14 calories. A costs $2 per unit and food B costs $1 per unit. How many units of each food should be purchased to keep a cost at minimum? Well, we want to minimize our cost, our price, when we purchase both of food A and B. Well, I summarize also information in this table. So let's consider first variable x, the number you need for b, and y, the number you need for a, yeah, x for a and b, and y for b. Well, this information we have the vitamins for in food A we have 15, and for B we have 20. Minerals we have 13 in food B and 20 in food B. Calories we have 10 in food A and 40 in food B. The cost per unit we have $2 for food A and $1 for food B. Well, our objective here is to minimize the price at one. How much I will cost for me this both books. Well, C equal to x plus 1 equals to $2 for A and $1 for B. Well, this is the constraint we have. 50x plus 20y will equal to 1040 units because at least content 1040 units for vitamins and 108 units for mineral and 100 2000 100 200 units for calories. So based on this constraint, so we have here 13x plus 30x plus 20y will equal 108 units, 1008 1800 units, and for 10x plus 40y will equal 1200 units in calories, and x of y shall be greater, of course. Well, let's continue here. We are writing all algorithms. We apply our solver here. We want to minimize this problem. We minimize our variables x and y both, which is low bound because it will be equal to or greater or equal to 0, and I will write in my object function here is to x plus y 1y, sorry. Well, this constraint we have 50x plus 20y greater or equal to 1040 units, and 30x plus 20y is greater or equal 1008 units. 10x plus 40y is greater or equal to 1200 units. Well, I apply my solver, and this is solution. Well, so we want to minimize this cost based on this constraint we have. So the optimal solution is 40, 45, and 105. Does mean the cost function is 105. The minimal cost is 105 when I ate 13 food A and 40 food B. 45 for sorry, uh, 8 30 food A. This variable should eat 13 unit, 30 unit for food A and 45 unit for food B to have this minimum cost 105. I hope that's clear for you. Well, so let's continue with the last example. An oil company has two refineries. Each day, refinery A produces 200 barrels of high grade oil, 300 barrels of medium grade oil, and 200 barrels of low grade oil. And the cost is 12,000 to operate. $12,000 to operate each day. Refinery B produce for refinery B each day produce 100 barrels of high grade oil, 100 barrels of medium grade oil, and 200 barrels of the low grade oil. And the cost is $10,000 to operate. The company must produce at least 800 barrels of high grade oil, 900 barrels of medium grade oil, and 1,000 barrels of low grade oil. How many days should each refinery be operated to meet the goals at minimum cost? So the objective here is to minimize the cost of the operation both of refinery. Well, I summarize the information here. We create the first variable y, number of operator referee B, and x for referee A, and the number of data referee A. So this is the constraint. Grade oil in referee A is 100, for referee B is 100, medium grade oil is 300 in referee A, 100 in referee B, and low grade oil is 200 in referee A, and 200 in referee B, and the costs here $12,000 and $80,000. The goal here is to minimize these costs. So the cost to operate this rain-free boat. Well, we create this constraint, here. 200x plus 100y is really required to 800 because at least we have 800 for okay, so at least we have 8,000 or 800, sorry, 800 barrel to hybrid oil and 900 barrel of barrel oil and 1,000 barrel of low grade oil. This is constant. At least, that's mean at least. So be so, so at least. Well, the same thing for medium grade oil. The same thing for low grade oil. So I apply again my optimizer. So minimize. So to minimize this cost, this is our constraint. 2000x plus 100y will equal to 800 300x plus 100y plus will equal to 900 and 2000 or 200, sorry, 200x plus 200y will equal 1000. Well, I apply again my optimizer and this is solution. So to minimize our cost, we should work 3 days in referee A and 2 days in referee B to have this minimal cost of $65,000. $65,000. This is the value, the low value for this minimal cost based on this constraint. So we should work 3 days in referee A and 2 days in referee B to have this low cost. Well, I hope that is clear for you all. Happy learning again and see you again.